Hello, this is a bonus video about some other methods or other approaches one can use when dealing with ordinary differential equations of order 1. We learned separation and also variation, but there are some other tricks. And essentially they were created by people who were desperate. Because today when you have a differential equation and it's not really all that nice, you simply work with it numerically. But before the advent of computers, essentially before the Second War, people simply had to use their brains to get some information from differential equations. And so they were using all kinds of tricks. They really spent a lot of time on it. And we could spend the whole semester just talking about those tricks, but most of them are extremely specialized. Today I want to talk about a few of them which may have, let's say, a slightly larger audience or larger target group. Let me go back to one of the examples which I used in my lecture on analyzing solutions. And I said that's an equation that we don't learn how to solve in this course, but it actually is solvable. And it looks like this. So what can we do with this equation other than separation, which obviously doesn't work? Well, there are several interesting types of differential equations that we can sometimes recognize. And one interesting type is so-called homogeneous equations. How do they look like? Well, these are equations which can be written in such a way that on the right there is some expression, but this expression does not deal with x or with y, but it deals with y over x as a unit. Does it work for our equation? By the way, we notice immediately that y should be different from x. That's something that we should keep in mind all the time. Well, I'm trying to achieve y over x in this expression, and I can achieve it easily. I just divide everything by x. So it's y over x divided by y over x minus 1. And we can see the expression now. The function capital F takes some variable, let's say w, and changes it into w over w minus 1. So that's the function. And if I substitute y over x for w, I get exactly this. Okay? So another way to see it is that when I look at this as a unit, then there can be no other x or y in the picture. And there is none really. So that's a homogeneous equation. How do we solve it? Well, there's a very simple trick for it. You take y over x and you call it z. That's another function of x, because there is little x here, little x here. Okay? Now, how do we apply the substitution to our equation? Well, the right-hand side is obvious. But what about the left-hand side? Well, there is an easy trick. We just imagine that x is x times zx, and we simply figure out what is the derivative. Well, the derivative of y by the product rule is simply z plus xz prime. And now we try to solve it. And essentially what's going to happen, this should lead to a separable equation. Let's see. xz prime is equal to z over z minus 1 minus z. Interesting. Let's moving a little bit more. I'm going to use common denominator here. So it will be z minus 1 and z on the top. And I'm subtracting z squared plus z. That's what it is. Okay, let me write it again nicely. xz prime is equal to 2z minus z squared divided by z minus 1. And that's a separable differential equation because I can move x to the right by dividing, I can move this to the left by dividing. So we actually know how to solve this one, and that could be the end of the example because we transformed the equation which is not separable into another which is separable. But just out of curiosity, let's try it. Okay, we have to be careful because when we are dividing, I don't want to have 0 here. So there are two stationary solutions. Z is equal to 0 and z is equal to 2, stationary solution. But we are not interested in z anyway, but just for the completeness. Okay, dz is multiplied by z minus 1 and divided by 2z minus z squared. That's on the left, and on the right there will be integral, and I'm moving x down into the denominator. Okay. Can I integrate on the right? Definitely. Can I integrate on the left? Not yet. This calls for partial fractions. Okay, I'm going to split this as z times 2 minus z. What happens? Well, I have to be careful. Perhaps I can make a little note here. Where do I get the coefficients? Over here, z minus 2. I cover it, I put 2 here, and I get 1/2. How about here? 0 is the root. I put it here, I cover up this. It's 2, negative 1/2. That's it. Do I like to have? Well, I'm not going to worry about it. I could simplify my life by multiplying everything by 2, but let's try to do it with it. Okay, I'm integrating this part, which is a nice shift substitution, but I have to be careful about the minus sign here. Logarithm 2 minus z. Another integration, another logarithm coming up. Another logarithm coming up. Plus c, so this is not logarithm. Okay, at least something. What next? Okay, I'm going to multiply everything by negative 2, definitely, and I'm going to connect the logarithms. So this becomes plus, they actually multiply together. 2z minus z squared. And on the right, it will be minus 2 logarithm x minus 2c. Now I'm going to use exponential, apply to the left-hand side and apply to the right-hand side, and then it splits into a product of exponentials. And I get rid of the absolute value using the plus-minus trick. Okay. On the left, 2z minus z squared. On the right, some constant d. And e to negative 2 logarithm x. What do I do with it? Well, for instance, I can take negative 2 and move it inside. So it's e2 logarithm 1 over x squared, which is 1 over x squared. Let's move on. Now I'm supposed to solve for z if I were solving just this differential equation, but in fact I'm solving a different one. So I will go back to my original notation. 2z is 2y over x minus y squared over x squared is equal to d over x squared. Do I like it? Reasonably, yes. Okay, I multiply by x squared, and perhaps I change the sign so that it's nice and I move everything to the left. So when I do that, I get y squared, because I change, okay, I'm writing it down. This one goes left, and I'm multiplying by minus x squared. So minus x squared cancels y squared here. I'm multiplying, it becomes minus 2xy, and I'm moving, it has a minus sign, and I multiply and becomes plus d. That's the formula for y. Okay, I'm going to use the quadratic formula. Y is equal to minus b plus or minus square root of b squared minus 4ac, so it's minus d, and divided by 2. Okay. And finally, I can write the answer, yx is equal to x plus or minus square root x squared minus d. Now, what are the conditions? Normally, I would ask for x squared minus d to be non-negative, greater than or equal to 0. But here's the tricky part. I have to remember that y should be different from x. So I need to make sure that this number is not 0. So x squared minus d should be positive. And that's the solution. Okay? Happy end. We can see that this differential equation was homogeneous according to the definition, and the substitution which was recommended to us actually led to the answer, which is nice. So that's the type called homogeneous equations. As you can imagine, this type is very, very sensitive. For instance, if instead of this y there will be just one, then the equation is no longer homogeneous. Let me show you. I could divide by x, of course, but then there's this problem with extra x. I would know how to get rid of that. So this one is not homogeneous. And that's one of the problems with those other methods. They can be very useful in some situations, but they are very sensitive. They only work to a very specific group. For instance, homogeneous equations, that's a very specific group. And in this introductory course, I decided to show just the methods which have, let's say, a wider field of applicability. They are, let's say, more useful in a way. But anyway, homogeneous equations, yeah, they do sometimes come handy. Okay, let's look at another trick. The next interesting group of equations is the exact equations. How do we recognize exact equations? Well, first of all, we should be able to write them like that. Some expression with x and y, and another expression which is multiplying the derivative, and perhaps something on the right which depends just on x. Some people actually prefer to put 0 here. It's possible, but this is more general. It may work better. Now, not every equation of this form is actually exact. There is one more condition, and the condition goes as follows. One should be able to rewrite the functions p and q as partial derivative of a certain function. Let's call it capital F, that's traditional. So this p should be in fact partial derivative of capital F by x, and this q should be in fact partial derivative by y. For some capital F. If this capital F exists, then it's called potential, but it's another theory. Why is it useful? Well, notice the following. This is in fact a function of x, because y is depending on x. It's a function. When I write f x y x and take derivative by x, how does it work? Well, there are two sources of x. So by the chain rule for partial derivatives, I have to differentiate by x, and I get here, or I differentiate by y and multiply it by the derivative of the inside function, which is y prime. So this exactly fits. That's the beauty. Such an expression can be written as just one derivative, and therefore, by integrating, we can recover fxy as the antiderivative here. And from this, with a bit of luck, we can recover y. Okay? So that's the general outline, how to work with exact equations. Now, how do you recognize whether this is actually true? That's a good question. There is a test for it. And the test is very simple. You simply take the partial derivative of p by y, and you compare it with partial derivative of q by x. And if they match, you've got yourselves a potential f. And then you have to find it, of course. This actually comes from complex analysis. Okay, let's have a look at our example. I look at it and I say, okay, does it have the right form? Well, first of all, I have to multiply y minus x y prime is equal to y. Okay, now we rearrange it. We get y, and I move it, minus y minus x, y prime is equal to 0. Does it have the right form? The answer is, well, actually yes. This is the p, and this, including the sign, is the q. Now let's make a test. P partial derivative by, here we go, p partial derivative by y gives me 1. Here, q partial derivative by x, when I differentiate by x, I get 1 as well. So this is an exact equation. That's a good news. By the way I remember it, there is y prime, and therefore I differentiate by x when I'm doing the test. It goes like complementary. Anyway, I'm looking for a function now. The function capital F, when I differentiate by x, should yield this part. I can see it over here. That's the pattern. So it should actually yield y. And capital F, when I differentiate by y, should yield, well, x minus y. Let me put it that way. Okay? Here we go. From this, I easily conclude that the function fxy should be an antiderivative of y, but with respect to x. So I'm integrating with respect to x to get x times y plus a constant. Now the trick is that I was integrating with respect to x, so I did not see the variable y. This part c could be a function of y. Let me check. If I take partial derivative by x, this becomes y, and this disappears. Yeah, it works. Okay, so that's my candidate, and I need to figure out the function cy. How do I figure it out? Using this condition. I take derivative by y of this expression, and I get x plus c prime y should be x minus y. I cancel, and I see immediately that cy is negative 1/2 y squared plus c, but I don't care about c because it would disappear anyway. I'm taking derivatives. Okay, so I'm ignoring c. This is allowed here, and I put together my capital Fxy. It's xy minus 1/2 y squared. Okay. This means that my differential equation here, hopefully, can be written like that. It's this expression differentiated is equal to 0. Let's check. I'm differentiating. When I differentiate by x, I should be careful because y is a function of x as well. So I differentiate. This is subtraction. I differentiate each side separately. Here I have to use the product rule. So first I differentiate the first part and I get just y, plus I copy the first part and differentiate the second part, which is y prime, minus. This is a composed function because it's yx, a function of x. Squared, I differentiate, so it's 1/2. Derivative of the square times I go inside and differentiate the inside function. So that's the expression on the left. And then when we rearrange it, we cancel here, we put the derivatives together, and we get exactly this. So yes, this equation can be actually written in this way. And now we just integrate. Very simple. So by integration, we get xy minus 1/2 y squared is equal to, I should put c here, but I'm going to put 1/2 c. Because I'm going to get rid of 1/2 immediately afterwards. Okay, I multiply everything by 2, I switch the sign so that it looks better, and I get y squared minus 2xy plus c is equal to 0. And if I'm not mistaken, that's exactly the same equation we had before, the only difference is that there was d here. So y should be minus this divided by 2 is x, this fits, plus minus this squared, yeah, it works. I can see there, x squared minus c, x squared greater than c. I can put it this way. So we are getting exactly the same solution as before using the homogeneous approach. Again, exact equations, that's something which is very sensitive to changes. Let's make a little change. This is still a homogeneous equation, so we could apply the homogeneous equation trick, by the way. Is this equation exact? That's a good question. So I'm going to multiply out, I'm going to move things about a little bit. y minus y plus x, y prime is equal to 0. That's the shape that we want to see. And now let's ask, okay, what is the partial derivative here by x? And the answer is the partial derivative by x is -1. What is the partial derivative here by y? And the answer is 1. And that's very unpleasant. I'm actually allowed to put some x's here, which means I can put them also here. Some expression with x, that's this rx here. But whatever x I put here, I would have to add it. Adding here, it wouldn't change the 1, because after differentiating by y, it would disappear. Okay? So that's something I cannot fix by playing with the right-hand side, unfortunately, in this way by adding. So this equation is not exact. Now, before the days of computers, people were really desperate to solve equations. So in a situation like that, they would start thinking, experimenting, doing all kinds of crazy stuff. And here is something which they came up with. This is not my invention. If you divide the equation by y squared, you get, now get ready for that, you get 1 over y minus 1 over y plus x over y squared, y prime is equal to 0. Now, is this an exact equation? That's a good question. Let's make a test over here. First, we differentiate by x, which is very easy. This goes away, and this is a multiplicative constant with the minus sign. Minus 1 over y squared. Is this differentiated by y giving the same answer? And the answer is yes. 1 over y, if I differentiate it by y, is -1 over y squared. So this is an exact equation. But this is really devious, isn't it? What if you don't have the right inspiration? Well, then you are out of luck. Well, let's try to finish it off. I think this is useful stuff. Okay, df over dx should be this part. So it means that f xy should be xy. Oops, I've been looking at the wrong place. Over here, I have to look over here. 1 over y. So df over dx is 1 over y. I integrate by x, and I get x over y plus cy. So far, so good. What's the second condition? df over dy should be this expression, minus 1 over y minus x over y squared. Let's put it all together. So, I am differentiating this by y, and when I do it, I get minus x over y squared plus c prime y is equal to minus 1 over y minus x over y squared. This cancels, and c should be negative logarithm y. And we end up with capital Fxy being x over y minus logarithm y. This is not very pleasant, so what we can do, we can split cases of positive y and negative y. So let's say that we play with just positive y for now. Okay, this looks okay, so I'm going to rewrite my differential equation according to the same trick here. Where is it? Over here. That's my differential equation, and it can be written as x over y minus logarithm y, and that all derivative. And again, you can check, if you differentiate carefully, you will get exactly this. We integrate with respect to x, so there will be a constant here on the right. And now we should solve this one for y. And that's where it all breaks down. This equation cannot be solved for y. End of the road. So the exact equation Actually, I could create it by forcing it, but then I was unlucky at the end, and this was all for nothing. Now, unfortunately, you run into the same problem, exactly the same equation, if you try to solve this equation through the homogeneous approach. You can rewrite it as a homogeneous equation, you can do the substitution, but at the end, when you're solving for y, the same trouble. In fact, this equation, although it looks almost the same as the previous one, cannot be solved analytically at all. So as you can see, solving differential equations can be very sensitive to even tiny changes. Okay, let's move on and look at our last example. Now, we saw this differential equation a short while ago, and I commented that it's not possible to rewrite it as a homogeneous equation. Is it exact? Good question. By the way, it's not separable either. Here we go. I multiply. And now I write it in the right form. Let's say this way. Or perhaps without the 1. I can keep 1 on the right and put 0 here. It will not make any difference, really. Okay, is it exact? I have to take this and differentiate it, well, including the sign, I have to be careful. Differentiate it with respect to x, because that's the y part. If I differentiate with respect to x, I get -1. How about this one? I differentiate with respect to y, and I get 0. So this equation is not exact, definitely not. However, if I multiply everything by e to -y, I get e to -y minus x plus y e to -y y prime is equal to 0. Why e to -y? Beats me. Somebody was desperate, trying all kinds of stuff and came up with this. And it worked. Okay, let's check. What happens if I differentiate this by y? Then the negative sign jumps out and I get this. So far so good. What happens if I differentiate this by x? Well, I can split it into two groups. This group doesn't have any x in it, so it disappears. And this is just x and a multiplicative factor and the minus sign. Yeah, it works. This is an exact equation. Well, let's see. df over dx should be e to -y. So fxy should be x e to -y plus some function which depends just on y. Now let's see what happens if I differentiate this by y. If I differentiate this by y, I get minus x e to -y plus c prime y. And this is supposed to be this expression, which is minus x e to -y minus y e to -y. Okay, this cancels. And I can see that the derivative is equal to minus y e to -y. Do I like it? That's integration by parts. Okay, so how do I integrate by parts? Okay, it's been a long while actually. Okay, I integrate this factor and I get y e to -y. Then I have to put minus integral, where this gets differentiated and this integrated, minus 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 e to -y. Does it work? Let me check. Derivative here puts minus and this fits. Derivative, derivative, and it fits. Now it should be okay. So that's cy. Okay, this comes here. And therefore, my fxy can be written as x e to -y plus e to -y plus y e to -y. And this, when I differentiate it, will create the left-hand side of my equation. Where is it? Here, the left-hand side of my equation. And this should be 0. So I integrate, I obtain a constant c here, and I get, how will I write it? Let's say this way. x e to negative y plus y plus 1 e to negative y is equal to c. Curiouser and curiouser. Okay, I multiply everything by e to y, and I get x plus y plus 1 is equal to c e to y. And now I'm supposed to solve this for y. And I can't, because there is y mixed in the equation and e to y as well. These equations cannot be solved. They are known and they are studied. So mathematicians know quite a lot about solutions of such equations. The solution depends on x. X is a parameter. So mathematicians actually introduced a special function, which is called Lambert function, I believe. And it shows the solutions depending on the x. So it can be used as a function. I can use it as a name. I can say y is equal to Lambert something, but we don't have a formula for the Lambert function. So even if I write it, it will not be an algebraic solution for my equation. In fact, this equation cannot be solved algebraically. That's another of those really bad equations, although it's really, really simple. Let's try one more approach. Something that we didn't see before. And it's a bit tricky, but it's nice. Now let's have a look at the original equation again in this form. What really bothers us is that x plus y is in the denominator. Okay? Here is a trick. I do something like 1 over, which is not really allowed with the differentials. You can imagine that I divided both sides by dy, multiply by dx, multiply by this. I just rearrange the equation. This can be done in a proper mathematical way by referring to the theorem about derivative of an inverse function. But it will take half a blackboard or something like that to do it really properly. This is the applied way. People from applications, they are more free with mathematical tools. And yeah, they just flip it around. This is a much nicer differential equation. And notice that we have a change of setting. Now x is understood as a function of y. So we are really working with the inverse function. We are assuming that the solution, if it exists, well, it does exist as a Lambert function. We assume that the solution is actually invertible, and we are looking for inverse function. That's a very nice differential equation. If you feel uneasy, it may be actually better to use another variable instead of y, because we are used y to be function. So let's say this one, dx over dt is equal to x plus t. That's a very nice differential equation. It's a first-order differential equation. It's not separable, but it can be solved by variation. And in fact, that's one of the examples that we do when we are learning variation. So we should be able to write down the answer. Let me put it with y so that we know what's happening. xy is equal to, now there should be first the solution of the homogeneous part, which is obviously an exponential. And then there is the other part that comes from variation. So my equation now reads this. And we are trying to solve it for y. Now, by any chance, is it the same equation as we had here? That's a good question. Let's see, x is equal to c e to y minus 1. Yeah, it's the same equation because it's the same problem, underlying problem. I'm trying to describe some phenomenon or something here, and this phenomenon is described by this equation. So that's why I ended up with it twice already. We cannot solve it. Dead end. But this is a really interesting idea, and sometimes it works. You have to be really, really lucky for this to work, actually. Happens, or not. And that's about it regarding some other methods, especially the homogeneous equations and the exact equations. They are in some applications quite useful. But I didn't want to talk about it in my course because this is really like a bonus stuff. This is just an elementary introductory course. So we can just imagine that I didn't do anything here. That I haven't even been here. But one of these days, if you happen to meet homogeneous differential equations, or if you encounter somewhere on the internet the words exact differential equation, then you may perhaps remember, you come back here, you look it up. That's it.